In this video, we will be looking at how to graph polynomial functions using transformations. Now, when we have a polynomial function, and we will be focusing specifically on cubic and quartic functions, they have to be in that nice transformed format where we have the a, the k, the d, the c values. So first thing, we're going to refresh on what each value represents. Then I'll show you the mapping rule, and then we'll apply it. So here is your transformed notation. If your a value is negative, so like right here, that means that there is a reflection over the x-axis. After that, look at the absolute value of a. This is the value that all of your y values will be multiplied by. So if it's a number greater than 1, you're making the numbers bigger, so it's a vertical stretch by a factor of a. If it's between 0 and 1, you're making numbers smaller. Like if I multiply something by a half, I make it smaller. So it's a vertical compression by a factor of a. So this first part here is a vertical transformation. Now we have another vertical transformation, and it's the c value at the end. Notice the vertical transformations are outside that function notation. And this value at the end is the vertical shift, so the up-down value. So if it's positive, you're shifting up c units. If it's negative, you're shifting down. Then we have all of the horizontal things inside the function here, which is replacing what x normally would be in f at x. And these values will affect the x coordinate. So if this k value is negative, that's a reflection over the y-axis. For the k value, we actually have to take a reciprocal of k. So we have to look at the value of 1 over k. And if 1 over k is greater than 1, we have a horizontal stretch by a factor of 1 over k. If it's between 0 and 1, we have a horizontal compression by a factor of 1 over k. And finally, inside the bracket, we also have this x minus d. That d value is the horizontal shifting, the right-left. Whatever value you see in here, you have to take the opposite sign, and that's the direction you are going in. So if we saw x minus 2, we're actually shifting to the right, positive 2. If we saw x plus 3, we're shifting to the left 3 units. Okay. Now, the way we're going to graph really all of the functions in this course is using the mapping rule. And we're going to start with the base function. So it might be the x cubed function or the x to the 4 function. And we're going to create a table of values from x values of negative 2 to 2 to find 5 coordinates, let's say, on this original parent function. Then we're going to take these coordinates and run them through this mapping rule. And here's what the mapping rule says. All the horizontal things affect x. So x would be multiplied by whatever that horizontal compression or stretch or reflection factor is. So it's going to get multiplied by the reciprocal of k. And then you're going to add or subtract whatever that shift value is. And your mapping rule is always exactly what the transformations are. If I'm going to the right 3, I'm going to add 3. If I horizontally stretch by 2, I'm multiplying by 2. And then same thing with the verticals, they affect the y coordinates. So that's the a and the c values. So let's put this into action. So here I can see that my parent function is y equals x cubed because of this exponent of 3 on the outside. So that's going to be important for my mapping rule. But I do want to state the transformations first. So I'm going to start with this 2 out front. That is a vertical. If I multiply something by 2, I'm making it bigger. So a vertical stretch by a factor of 2. Then I'm going to go inside to the k value. We always want to state our transformations in the order that they would apply. And we kind of follow BEDMAS. Things attached by multiplication go first. Things attached by addition and subtraction go last. So first I notice this negative, so that is a reflection. and I'm reflecting over the y-axis. That way it is a horizontal transformation. If I have something here, when I reflect it over y, it ends up here. That looks horizontal. Then I'm going to look at the k value, the absolute value of the k, which is a half. But remember, we have to take the reciprocal. So even though I see a half, I'm actually going to be multiplying by 2. And if I multiply something by 2, I'm making it bigger. So that is a horizontal stretch by a factor of 2. And then I can finish off with my shifting. Here I see x minus 4, so that actually means we're going to the right 4. So shift right 4 units. And then the plus 5 at the end, right here, is a shift up by 5 units. And now that we know our transformations, we can get onto our mapping rule. Now I'll just write the mapping rule first and then I'll do my table of values just because I have the transformations fresh in my head. So I'll have a table of values here for my base or parent function. So I'll do that there. But my mapping rule that I'm going to run my coordinates through, so we had a reflection over the y-axis, which means my x value will turn negative. We also had a horizontal stretch by a factor of 2, so x will also get doubled. Then we were shifting to the right 4, so plus 4. So you'll notice that, yes, these values are the opposite from what's actually happening inside the bracket, but they perfectly match with the transformations that we wrote right here, okay? And then for the vertical, we're stretching by a factor of 2, so the y will get doubled, and then go up 5, so plus 5. All right, let's get that base function now. So when you're doing a table of values, remember, you can pick whatever x values you want. I like a little bit of symmetry, so I'm just going to go from -2 to 2, some negatives, some positives, and now I'm just going to run them through x to the power of 3. So -2 to the power of 3 is -8, -1 to the power of 3, -1, 0 cubed, 1 cubed, 2 cubed. Now I have my starting coordinates, okay, and now I'm going to run them through the mapping rule. So I'm going to start off with this -2, and I'm going to replace the -2 in this x. So it's going to look like this. -2 times -2 plus 4. So that's 4 plus 4, which is 8. I'm going to do the next. I'm just going to do all the x's first. Now I'm going to take the -1. So -2 times -1 plus 4, that's 6. Then -2 times 0 is 0, plus 4 is 4. Then the 1. -2 times 1 is -2, plus 4 is 2. -2 times 2 is 0, -4 plus 4 is 0. I have all of my x coordinates. This is where they've all been stretched, reflected, and shifted to. And now I'm going to do the same thing to my y. So I'm going to start with the y value of -8, and that's going in here. So 2 times -8 is -16, plus 5 is -11. Then 2 times -1 is -2, plus 5 is 3. 2 times 0 is 0, plus 5 is 5. 2 times 1 is 2, plus 5 is 7. 2 times 8 is 16, plus 5 is 21. And now I can plot my coordinates. And my coordinates will be 8, -11 for the first one. So it's just going to go a little bit off the page right here. 6, 3. Here it is. 4, 5. Here it is. 2, 7. And 0, 21 is off the page. And then, you know what, when you look at this, you might not know exactly what the shape should look like. So if that ever happens, draw out what the base function should look like, and then you kind of know what that general shape should be. So I should have done this before, so I'm just going to leave these red ones for now. I'm not going to connect the dots just yet so that we don't do something funky, and I'm going to plot these coordinates here. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. And here's what the original x cubed function looked like. Okay, so if you look at it, we actually see that there's a point of inflection at the origin because the concavity is changing. We have this concave down on the left, concave up on the right, so I'm expecting something similar. Now, this point here, that was at the origin, that point of inflection, where did it go? It went to 4, 5, which is right here. So I'm expecting that point to also have that swap in the concavity. So there we go. Roughly, this is what that transformed function will look like. And there it is. We practiced our transformations, we did our base function, we did our mapping rule, we sketched it out. In terms of the domain and range, nothing too fancy here, just negative infinity to infinity for both domain and range, or if you like the other notation, XER, YER. Okay? And now, let's do the same thing on a quartic function. So this is to the power of 4, so that's how we know that the base function is going to be y equals x to the 4. So you know what, this time I'm going to change up the order. I'm going to start with the base function, table of values, and graph, then I'll state the transformations and do the mapping rule. So starting with the same negative 2 to 2, negative 2 to the power of 4 is positive 16, negative 1 to the 4 is 1, 0 to the 4 is 0, 1 to the 4, 1, 2 to the 4, 16. And I'm going to go ahead and plot these points. Now, I'm not going to have really too much to plot here, unfortunately, because 16 is off the page, but we'll just do a dramatic increase here. Okay, so there's my base function. It looks like a parabola, really, just more stretched out, kind of. So now my transformations. We have a negative value here, which means it's a reflection. But because it's with the a value, it's vertical, because it's outside those brackets, so reflect over the x-axis. So I'm expecting this to end up going downwards. Then we have the 3, that's a vertical stretch by a factor of 3. Notice I'm not saying by a factor of negative 3, the negative is the reflection. Then we have, okay, something funky is happening inside the bracket. I have this 2x plus 2, but in order for us to state the transformations properly, the k value has to be factored out. So I'm actually going to rewrite this. Keep the negative 3, open up a square bracket, and imagine dividing both the 2x and the 2 by 2, and we're left with x plus 1. Now it's all to the 4 minus 1. So what we actually have here, this 2, remember we take a reciprocal, so it's a horizontal, and if it's a half, I'm making things smaller, so a horizontal compression by a factor of 1/2. Then we're actually shifting left 1, not left 2. So factoring out that k is very important. And then the minus 1 at the end is a shift down 1 unit. Okay, and now we could write out our mapping rule because we have these nice transformations. So horizontal, it was a compression of a half, so 1/2 x. We're going to the left 1, so minus 1. We had a vertical reflection and stretch by 3, so negative 3y. And we're going down 1, so minus 1. And now, let's plug into our mapping rule. So I'm going to start with x is negative 2. So a half times negative 2 is negative 1, minus 1 is negative 2. Just plugging in here. A half times negative 1 is negative 0.5, minus 1, negative 1.5. A half times 0 is 0, minus 1 is negative 1. A half times 1 is 0.5, minus 1, negative 0.5. A half times 2 is 1, minus 1 is 0. So we have all of our x's, and now time for our y's. So I'm going to start with 16. And we're plugging in right here into the negative 3y. So negative 3 times 16 is negative 48, minus 1 is negative 49. And it's going to be the exact same as the last one, so I'm just going to go ahead and write that on. Then negative 3 times 1 is negative 3, minus 1 is negative 4. Negative 3 times 0 is 0, minus 1 is negative 1. And then for the 1, it was the same thing as before. Okay, going to go ahead and plot these points. Now, the first and the last one, unfortunately, are off the page, so can't do that. Negative 1.5 with negative 4, negative 1 with negative 1, negative 0.5 with negative 4. And there we are. There's our transformed function. And here our domain and range aren't as basic, so I'll just write them down. Domain is negative infinity to infinity or XER. But for our range, we're going down to negative infinity, but the highest point that we reach is negative 1, including that value. You could also write it as YER, y is less than or equal to negative 1. And there we are. And this mapping rule that we've just looked at can apply to all of the functions we'll be looking at in this course. It applies to exponential, it applies to logarithmic, it applies to sinusoidal, and so on.